So today we are going to do last two topics of this unit, and then we'll start unit 4. One is photoelectric effect. Anil, we did this earlier in unit 1 when I was teaching you about emission absorption spectrums. Any idea, Anil? Oh, okay, you cannot. Oh, okay, fine. So I think we have to do it, photoelectric effect. Yeah. So we are starting with the class. So 3.12 photoelectric effect. What's the meaning of photoelectric effect? First, I'll tell you the meaning and then we'll see the explanation part and we'll do some questions. The meaning is that when you take a metal and when light is falling, photo means light. When light is falling on the surface of metal, this is a metal. We have selected a metal here because metals, they lose electrons very easily. So when the light is falling, light is in the form of photons, HV. They are like photons. When the light is falling on the surface of metal, okay, Anil. So metals, they lose electrons very easily. You know that metals have low ionization energies, so they lose electrons easily. So this light will hit the metal atom, and light is a form of energy. So electron jumps out. Electron is coming out. This is called as photoelectric effect. So we are going to observe this photoelectric effect on the surface of metal because metals can lose electrons easily. Photo means light, electric means electrons, and how this light and electrons are interacting with each other. To show you this photoelectric effect, this experiment was done by Einstein. You are already aware of his name? Very famous scientist. Okay, so to understand this photoelectric effect, let's have a review of the Planck's equation. The light which is coming from the surface of sun or light from anything which is giving you light, the energy of that light is equal to hv. H is called as Planck's constant. See this equation? H is the Planck's constant which will be given to you in the exam like this. But what is V? V is the frequency of light. Frequency. So if frequency is higher, what happens to energy? If frequency is high, energy is high. See, they are directly proportional. So I can say that energy is directly proportional to frequency. So if frequency is high, energy is high, right? Aditi, you can also answer here in the chat. Okay, so now this HV is also called as a packet of energy. It's a packet, fixed amount of energy. The other name is photon. It's a photon, which we did in earlier unit 1 also. So what are photons? Photons are the packets of energy. And light is coming, sunlight, any light, which we are making like this, like a wave. But it is actually also like packets of energy. Each packet of energy is calculated by HV. So if these are photons, each packet is called as photon. Every photon has a fixed amount of energy with it, which is also called as quantized. So we did the quantum numbers in unit 1 based on this concept that the energy here is quantized, fixed. It has a fixed quantity of energy. So energy which is falling on the surface of metal, this is metal surface. The energy, the light which is falling on the metal surface is in the form of quanta, or it is quantized energy, right? Any question here? This is the review of the Planck's equation, Planck's constant. No question? Aditi, any question from your side? Okay, good. Aditi, you have to answer in general chat. Now let's try to understand photoelectric effect, and we are going to do some questions based on it. This was the setup made by Einstein. And he said when light is falling on the surface of metal, this is metal surface. Metals have low ionization energies. The light is falling, an electron is going to jump out. Electron is jumping out from the surface. Electron is attracted to the nucleus. You agree with that? This electron is attracted to the nucleus. When this photon HV, this is HV, when the photon is going to hit the electron, the energy of the photon is transferred to the electron. An electron is going to break these attractions. Is going to break the attraction because it's getting energy to break the attractions with the nucleus. And then is going to moving out. It's moving. So this energy, which is falling on the atom, HV, we can call it as V0. V0 means incident light, the light energy which is falling. Incident light is doing two things. You can see two things here. One, overcoming the attraction. Overcoming the attraction of the electron with the nucleus. Second, kinetic energy. So this energy is going to do two things. One, overcoming the attraction, we call it as binding energy. It's going to break the attraction, and the energy needed is called as binding energy. And then the electron is moving, is called as kinetic energy. So this photon is getting converted into two parts. The energy is used in two parts. One is binding energy, other is kinetic energy. Binding energy also you can calculate as HV, as a photon only. Some part of the photon, this is the incident, HV naught. This is the total, the one which is falling, total, falling on this metal surface. So this is the metal surface, simple picture. Light is falling on it. What's the energy of this light? HV naught, right? Now, this energy is gained by electron here. Electron is bound to the nucleus. So the energy is breaking this attraction, which we are calling it as binding energy. Let's say HV is the amount of energy which is used to overcome the attraction, and kinetic energy is half mv squared. This was the equation given by Einstein. Any questions here, children, about this equation? Okay, good. Now, but why are we learning? So how come Einstein is so popular only with this equation? No. Einstein is very popular because he was the first one who described the dual nature of light. Light has a dual nature. Dual nature means it's going to have a particle nature and a wave nature. Light has particle as well as wave. This was proved by Einstein. Okay, let's see how. I give you a marble. What is marble? Marble is a particle. It has mass, right? This is another marble. Marble, the one which we are using for games. You hit this marble, take this marble and hit this marble. So when this marble is going to hit this marble, what happens to this marble? It moves. That proves that marble has a particle character. A particle hitting another particle and they move. But here, this light is hitting this electron. An electron is moving. What is electron? Electron is like a particle. It has, though it has negligible mass, but it's a particle. We know that, right? But light when it's going to hit the electron is making this electron jump out, just like when a marble hits a marble. So it means light is also like a particle. So this was proved by Einstein that light has both the natures. It has a wave character, is moving like this, like a wave, and it has a particle character. And particle are, what are the particles here? Photons. These are the particles, HV. So when this electron is hit by this photon, which is of energy HV, then electron is going to gain this energy and is going to jump out of the atom, gaining the kinetic energy. So electron is moving. It means light is behaving like a particle. So light has a dual character. Are we okay with this? Dual. Dual means double. This photoelectric effect proves that light has dual character. You remember, children, one more equation? I think you must have heard about this equation. MC squared. You know this equation? How many of you know this equation? Who gave this equation? Do you know the name of the scientist? This is? Yeah, Einstein. He gave this equation. And what this equation is saying? Check. This is energy. This is mass. This is speed of light. According to this equation, you can convert mass into energy. And you can convert energy into mass. See, that's the meaning of the equation. And that this can be the starting of the universe. Initially in the universe, there was only energy. And then that energy was converted into mass. And from that mass, other masses, shapes, different organisms, different planets, universe is made. So maybe this is the starting point, the conversion of energy to mass. Or like in nuclear plants, you must have heard about nuclear plants. What is happening in the nuclear plants? You are converting the mass of the radioactive material into energy. You're getting energy there. We are using, yeah, fission and fusion. Yes. So what is that? In that case, we are using radioactive materials like polonium, uranium, like this, the one which are very heavy metals at the in the F block. They all are radioactive. We are using them. They are undergoing disintegration, and some mass of these substances is undergoing destruction. We call it as mass defect. Mass defect. Defect means this is the mass which is getting converted into energy. A small change in the mass will give you a large amount of energy because C is a big value. You remember the value of C? 3.0 times 10 raised to power 8. You are taking square of this. So even a very small mass can give you, very small change in the mass can give you a large amount of energy. That's why these nuclear reactors, they give us so much energy. We are converting that energy to electricity. Country like France, they are using only these nuclear reactors for their electricity. They are not getting electricity from anything else. Like in other countries, we are using different sources, like we are using water also. But France is completely based on nuclear power plants. So you can understand the importance of energy here. This, what I discuss, is just a simple knowledge as a chemistry student. It's not the part of your AP. So we can come back to the photoelectric effect. Light has a dual character. So photon is a particle. See? So what's the formula of the photon, children? Can you give me the formula of the photon? Yes? Formula of the photon. Photon has a chemical formula. What is it? HV. This one. See HV. Aditi, try to answer here. Afan, your answer? Afan. Okay. More you write, more you speak on your side, whatever I'm speaking, and you feel that this is something new, speak that word very loudly on your side because you are muted. I cannot hear. You are not disturbing us. That's for your memorization or retention. Okay. So I already explained you this. So the light, the incident light is falling on the electron. The electron is overcoming the attraction. That is the binding energy. And the remaining energy is given to the electron as kinetic energy. So this is going to get converted into kinetic energy and the binding energy of, of the electron. You know, energy can neither be created nor be destroyed. First law of thermodynamics. So the whatever energy of the photon is falling on the electron, some is used in overcoming attraction and some is given as kinetic energy, right? So, so if out of these three, one, two, three, two will be given to you. One they will ask you to calculate. So that's the photoelectric effect. Now let's see some questions based on it. It will make you more, give you more better understanding of this concept. Read this question, please. Question one. So you can see the light. This is light, the photons. These are electrons. So the electrons are gaining this energy and they ejected from the surface, overcoming the attraction. And these are the wavelengths. You know that energy is equal to hv. You know this. And you also know that v times lambda is c. So you know that v is inversely proportional to lambda. You know this, children? So if energy is high, answer these questions. Aditi, any question, please keep asking your questions. If energy is high, what happens to frequency? What happens to frequency? It will be, yes, check the relation, direct, indirect. High, no, Lisa, direct. It's direct. And wavelength, see, wavelength and frequency. If frequency is high, wavelength is low. Remember this, plenty of questions are there on this. Aditi, you are okay with energy, frequency, wavelength? Naisha? Naisha, These things we have done earlier, Naisha, in the last class also, and in unit 1 also. Okay, so that's the basic background. Now read the question, please. So photoelectric effect is always on the surface of metals. We never discuss this on non-metals or something else. Can you give me the reason why? Why is Einstein selected metal as the surface for doing this photoelectric experiment? Why the metal? Why not something else? Any one of you? I started explaining this concept. Everything has metals, everything have electrons. Non-metal, they also have electrons. Okay, Aditi. Uh, they reflect light, Aditi, because of the photoelectric effect, you know. So Aditi, what Aditi is saying, children, the outcome of the photoelectric effect, when electrons are jumping out, going back, jumping out, that is the reason these metals, they shine. The shining surfaces, that is photoelectric effect. But the question is why it is more on metals? Yes, Anil is giving the reason, low ionization energies. You remember metals have lowest ionization energy. They can give electrons easily. You need less amount of energy. You take a metal surface, take a metal, gold metal, you take it in the sunlight, direct sunlight, and you put it in the direction of the light coming. You can see the shiny surface. That shine in the surface of the metal is the photoelectric effect by the sunlight, because metals, they can lose electrons easily. They have low ionization energies. Please write down these things. Okay, when the metal surface exposed to light, as the frequency increases, energy increases, they start getting ejected out. See, ejected out. And the energy of the photon is given to us 3.3 10 raised to power minus 19 joules. That's the energy given to us. Answer this. This energy is equal to, is the energy of the photon, is equal to hv. The value of h will be given to you 6.626 times 10 raised to a minus 34 joules seconds. The value of h is given. Can you answer here now? This question, they're asking frequency. Just plug in the values. Afan, pick up your calculator. Plug in the value. Plug in the value of h. They're asking V. So what is V? 3.3 times 10 raised to a minus 19 divided by 6.626 times 10 raised to a minus 34. Put it in parentheses. Take care of the units. Joules, joules seconds, joules cancelled. Frequency we know is per second. All these are per second. So units are not troubling us. Just get the answer then. So who is doing it? Aditi is saying C is the answer. Children, is she right? Please calculate. Afan, is the answer right? C. Yes, very good, Aditi. Perfect. Okay, now can we do the second part? Now you have the frequency. Afan, I cannot see your answer. You're not responding in the chat. You did? Okay. So frequency is this. Now you can use this equation that frequency times lambda is C, or you can use this equation. These equations will also be given to you in the exam, in the formula sheet. But still try to memorize them, practice them, so that you need not to go every time for the formula sheet. What is C? C, value of C will be given to you 3.0 times 10 raised to power 8 Take care of the units meter per second over lambda is equal to 5.0 times 10 raised to power 14 per second. So the equation can be given to you in this format or in this format. Now you can calculate lambda. Get the value of lambda here, children, from this equation. What's the value of lambda? Mhm. Mathematically, lambda is 3.0 times 10 raised to power 8 over 5.0 times 10 raised to power 14. This number in the denominator has to be in parentheses when you are going to plug in the calculator. This is per second. This is meter per second. Per second cancelled. What's the answer, children? The wavelength, lambda. 2 means zero point 0.2 units, meter, zero point 0.2 meters. But to know the color and to use this table, I need in nanometers. I don't think the answer is 0.2. Is it 0.2 meter? Uh, I think you want to say, okay, children, can you check this calculation? Because I don't think it's 0.2 meter. Azuni, can you check the calculation again? As it is zero point 0.6 times 10 raised to power minus 6. So actually it is 6.0 times 10 raised to power minus 7. Now, Aditi, meter, not nanometer. See, in the numerator, this is meter. The speed of light is in meter per second. So per second cancelled, you're left with meter. This answer is in meter. Now we know that 1 nanometer is 10 raised to power minus 9 meter. Plug in that ratio over 10 raised to power minus 9 meter. Meter cancelled. Your answer is 600 nanometer. 600 nanometer, come on this table. 600 nanometer is orange. Aditi, is it okay? No problem. See, Azuni, I said you have to put this in parenthesis. This is the children, most of the children, they do error. Afan, I again didn't get any answer, mathematical answer from you. This is 5.0 times 10 raised to power 14. So you have to put this in parenthesis. I don't know whether you placed it in parenthesis or not, right? I'm going to clear it. Ready for next question, children? Okay. This is the experimental setup which you are going to learn as Beer-Lambert's law. Beer-Lambert's. Right? So read this carefully. Okay, now this I will explain you in the next unit. If it is not clear, just leave it. Read this part. A wavelength of 510 nanometer, which is nearly approximately of the frequency this. What is the energy of one photon? Simple question, E equal to HV. H will be given to you. It is 6.6 times 10 raised to the power minus 34 units are joules seconds. Plug in that H value here, V value, and pick up your answer. Very simple questions based on this photon equation. In some questions, frequency is given. In some questions, wavelength is given. Here, frequency and wavelength, both of them are given. So pick up this frequency. 6 times 10 raised to the power 14. This is joule seconds. This is per second. Per second, second cancelled. Answer is in joules. What's the answer, Azuni? Afan, what is the answer? Just multiplication. Somewhere around 3.6. Yeah, okay. Yeah, Azuni is saying D, children. Yeah, okay, good, good, Azuni, good, Afan. D is the answer. I also agree with her. Very good. So these questions are very simple, and I'm not going to waste more time on these questions because they are just the equation E equal to HV. E is given, get the V. V is given, get the E. V is given, get the lambda. Lambda is the wavelength. Now these are slightly different. Let's focus on these questions. It takes 208.4 kilojoules of energy. So what is this? Energy. E. This one. Kilojoules. Kilojoule is not the SI unit. 1 mole of electrons. So number of electrons are 1 mole, means Avogadro's number. From an atom on the surface of rubidium metal, how much energy does it take to remove a single electron from the atom on the surface of rubidium atom? This is very simple question. How many electrons we are removing? 1 mole. So number of electrons are Avogadro's number. Yes, Aditi, Anil. Yes, good. Number of electrons are Avogadro's number, which is 6.022 times 10 raised to the power 23. But the total energy which is needed, total energy, total E is 208.4 kilojoules. That is for all electrons. So for one electron, each electron, it will be 208.4 divided by Avogadro's number. Is it okay? And what will be the units now? Like this has a unit of kilojoules per mole. But now the unit will be kilojoules. No, no, no. I didn't convert kilojoules to joules. I'm still working with kilojoules, Anil. It's still kilojoules. And this is a number, has no units. These are the number of electrons, right? So can I say kilojoule per electron? Yes, yes. Kilojoule per electron. So please focus on this unit part also in every question. Are we done with this? Lisa, is it okay? Is it clear? Okay, and Anil has already calculated, and that energy he is saying us 34.6 times 10 raised to the power minus 23 kilojoules per electron. Can you put this in scientific notation? Put this number in scientific notation. Is it right? Scientific notation means bring this decimal after first non-zero digit, means on this side. Make this big number small number. So this minus 23 will become minus 22, right? This we discuss in zero unit. Scientific notation. Now, can you convert this into joules? Joules means 1000 joules are there in 1 kilojoule. So multiply by 1000. Put this number in scientific notation. Yes, Anil. Good. Only Anil is doing it with me. I hope rest of you are understanding this. So I'm just trying to take your attention to the units. I'm just trying to show you that units are very important in your free response or multiple choice questions. And AP is very much interested that you should understand your units clearly, right? Okay, now let's do the next part. Aditi, units are clear? The next part. What is the maximum wavelength of light capable of doing this? Okay, now before you answer this question, write down in your notes that when the metal surface is exposed to the sunlight, one photon, one photon can eject only one electron. Photon is like a particle, like a marble. A marble is going to hit one marble, right? So there is a marble, I'm going to hit one marble with one marble. So photon is like a particle, so it's going to hit only one electron. So one photon is for one electron. So it means to know the wavelength, I need to know the energy of one photon. Do you have the energy of one photon? Do we have? Yes, this one. This is for one photon, isn't it? Now you can understand why we were doing all these things. So, and joule is the SI unit. That's why I converted kilojoules to joules. Because H, the value of H, which will be given to you, the units are joules seconds. So this E should be in joules, right? So it is 3.46 times 10 raised to a minus 19 joules. So what is V? 3.46 times 10 raised to a minus 19 joules divided by 6.626 times 10 raised to minus 34 joule seconds. Joule and joule cancelled. Your answer will be per second. Frequency is per second, SI unit. Can you work out this answer, children? That's the frequency. And that answer is Azuni, Afan, what's the answer? What is the answer? Yeah, we can do that. Once you get the frequency, then frequency is equal to C over lambda. You can rearrange that. So lambda is equal to frequency, C over frequency. So I need frequency, right? Okay, let's see. Aditi is saying, Azuni Aditi. Okay, yeah. 5.22 times 10 raised to minus 14 per second is the frequency. So lambda will be 3 times 10 raised to, and what are the units of lambda? That you are going to take from the speed of light, meter, divided by 5.22 times 10 raised to minus 14 per second. Lisha, you also do the calculations. She's doing okay. Answer is in meters. Yes. And how much meter we are getting? How many meters you are getting? And if it is needed, we can convert that into nanometer. Can you convert that into nanometer? Can we check whether it is colorful or not? Because visible light, visible, the wavelength is in the range of 400 nanometer to 800 nanometer. This is the range of the visible. You know, some metals, they reflect colorful lights. The light reflected by gold is nearly yellow. when you put the strong light on it. The blue color reflected by some metals. So Anil is saying lambda is 1.9 times 10 raised to power minus 15 meters, which means 1.9 times 10 raised to power minus, how much is this? Minus 15 plus 9 is 4, 6, right? Nanometer. Azuni is saying she's getting only 5.45. But Azuni, did you check this is minus 19 and this is minus 34? How come this can be 1? Yeah, okay, check that. So this doesn't fall in the visible light, right? You're wrong. Okay, so please give me the right answer. Lisa, Aditi, can you do this calculation and give this answer? Aditi and Lisa are giving me 10 raised to power 21. Yeah, I think they are right. Because this is 8 plus 8 minus 14 is going to be 22. 3 divided by 5. So they are right. This answer is not right. So you didn't place the parenthesis then. Anil, that's, I'm telling you from the starting. The denominator, all the numbers should come in the parentheses. Otherwise, you'll get the wrong answer. So answer is 5.74 times 10 raised to power 21. Were you writing 21? You were not writing 21. You were not giving this number. Okay. Now this is meter. Convert this into nanometer and definitely it is not in the range of visible light. So we are good with this. Can we do this question? Read the question with me and I'll ask questions. Please try to answer them. This is multiplication. Carbon, we know what is carbon, right? C is absorbing energy, wavelength this. So can I calculate energy if I know the wavelength? You cannot see the new question, Anil. All of you can see this new question, children? Anil, you rejoin then. Okay, you can. So E is equal to HV. That we know. But we also know that V is equal to C over lambda. So can I write HV as HC over lambda? Can I write like this? Afan, is it okay? So energy can be calculated from the frequency and energy can be calculated using the lambda. So E is HC over lambda. I'm going to use this equation. I have the value of H will be given to you also. 6.626 times 10 raised to a minus 34. Any idea what are the units? Joules second. See the speed of light, which you must know, but it will be given to you. And the units, take care of the units, children. Meter per second divided by lambda. Lambda is 150 nanometer, but that will not work. This is meter, this is nanometer. So I have to convert this nanometer into meter. And we know that 1 meter has 10 raised to power 9 nanometer. We know this. Nanometer cancelled, right? Now solve it. This per second cancelled. All the units are getting cancelled out. Meter cancelled, and you're left with joules. And that's the unit of energy, joules. Please get this answer. What is the answer? And give me the right answer in one go. So I will wait for minimum 2, 3 answers. Yes, I'm also getting the same. So answer is 1.33 times 10 raised to power minus 18. Units are joules. Yeah, right. Good, Afan. So this is the answer. But is this the energy needed to remove 1 mole of electron or 1 electron? This energy. Are you using 1 photon or 1 mole of photons? You're using 1 photon. So this is the energy per electron, correct? Per electron, per atom. Right now, we can say per atom because we are dealing with carbon atoms and we are saying the 1 photon is falling on 1 carbon atom. So 1 electron is getting ejected. So it is per atom. Is it okay? Now read the next line. This one. So this is per atom. The next line is also confirming it. They are saying that 1 atom is absorbing 1 photon. This line is saying that. But how much is the total energy emitted? How much is the total energy? The total energy which is given to me in the question is 1.98 times 10 raised to power 5 joules. And how much per atom? This much. So the number of atoms are the total energy which is given to you for the complete sample. The complete sample is going to take this much energy divided by energy of 1 electron, energy per atom, the one which you calculated. Just plug in the values. Total energy is 1.98 times 10 raised to power 5 joules and 1.33 times 10 raised to minus 18 joules is the energy per atom. How many atoms I'm getting? Atoms, Anil. Because they are saying 1 photon represents 1 atom. So how many atoms we are getting? 1.5 times 10 raised to power 23 atoms. If they say rather than number of atoms, they are not asking number of atoms, let's say they are asking moles of atom, moles. So you reach up to here to the number and convert that into moles. So you divide this by Avogadro's number. Sig fig Naisha, you check how many are there in the question. This is multiplication. How many sig fig here? 3. So this answer is in 3 sig fig. How many sig fig here? 3. 3. So answer will be in 3 sig fig. So I think we have written in 2. We need one more number. So Naisha, she's checking us. She realized that we have not given the answer in right sig fig. So what is there after 1.5, Anil? Only Anil is doing calculation. You know, he's in the flight also. He has internet issues right now. So 1.49. Yes, yes. Now, can you convert this Aditi into moles? Get the moles. To get the moles, we have to divide the number by Avogadro's number because Avogadro's number represents 1 mole. So how many moles? Anil, if you are taking it as exactly 1.5, then take it as 1.50. 3 sig fig. That's the only problem we faced. Otherwise, there will be hardly any difference in the answer. Answer will be same. So, and AP is very particular for sig fig in free response. So how many sig figs again, Aditi? 3. Go for 3. Don't count this 0. After decimal. 2, 5. Is there any number after that? 247. Okay. But if I say no, I want to know the grams of carbon. What is the mass of the sample? Mass of sample of carbon. Then what should I do? Then you will take this 0.247 moles and multiply it by molar mass, 12 grams per mole. Lisa, is it okay? You're comfortable with this? Lisa, okay. Now moles and moles cancelled. And this will be your answer. And again, place the answer in 3 significant figures, which Aditi is giving as 2.96 grams. Good, very good. Perfect. Okay, this is the question, another type of question. So in these questions, we are using wavelengths, frequencies, photon, and we have to understand that one atom, one electron, one photon. Two atoms, two photons. 1 mole of atoms, 1 mole of electrons, 1 mole of photons. So you should know this equation also. E is equal to N HV. Please write down this equation. What is N here? Is the number of atoms or electrons. Number, not the moles, number. Yes, you have to, like Aditi is saying, when we are going to check the sig fig. So she's just asking a simple question. Do we have to round off the last digit? So what's the answer, children? Like for example, Aditi, if the answer number is this 1.998, I want you to put this number into 2 significant figures. What does it mean? It means you have to drop this 98. This 98 is more than 50. You're going to add 1 into it. When you add 1 into it, this becomes 10. So Lisa is answering 2.0. Is this the question, Aditi? Okay, good. Perfect. Okay. So this topic is done. It's a very important topic, very simple. Every time we are using that Planck's equation, frequency, wavelength, speed of light, these kind of relationships, right? Now we are starting the next one, the Beer-Lambert's law. Beer-Lambert's law is a kind of lab. It's a AP chemistry lab. It is used to calculate the concentrations. So please understand the important points. Concentrations of solutions. First thing, we are calculating the concentrations of solution. We are using the concept of light. Light means that photon HV. So this lab is based on absorbance of light. Absorbance of light. That's why it is here in this unit. And from this absorbance, we are going to calculate the concentration. If I represent absorbance of light as A is the absorbance, then this A is equal to one constant, we call it as epsilon. It's a Greek letter again. C is the concentration. L is the length of the that's sample tube. You'll understand this. So we'll be using this equation. Then we are going to make a graph of A versus C. Then as the concentration increases, absorbance increases. You see direct. It's a linear line graph. And from this graph, we are going to work out the concentration of our unknown solution. So I want you children to pay attention to everything. It's something new. I will be teaching you a few new equations, but half of the things are based on what we have done earlier. For the concentration of the solutions, we are going to use molarity. Molarity we know. And we are also going to use dilution law. We'll use dilution law here. So what is dilution law? Can you type the dilution law here, children? The moles before dilution, the moles after dilution, they are going to be same because during dilution, we are only adding water. Yes, Aditi. The dilution law is M1 V1 equals to M2 V2. So we will work with this equation. We will work with this equation. We'll make this graph and we will calculate the concentration of the solution. This is the lab. And I'm sure that your teachers are going to give you this lab in your schools. And it's a very simple lab, but it is based on your understanding of the molarity, dilution law, and light. Let's start. So first thing is, we are going to use the relationship between absorbance and the concentration. The meaning of everything is given here, but I'm going to show you one picture of the instrument. In the instrument, there is a place where you are going to insert sample tube. This is sample tube. Sample tube has a particular length in centimeter. So this L is the length of the sample tube. And you have your solution. Your solution is present in this sample tube. This is the solution, right? Let's say with C concentration, C. In molarity, moles per liter or molar, right? The length of the tube, this is the sample tube. Length of the tube, you are measuring it as L in centimeter. So these two things are clear. This is the sample tube, right? And here you are going to expose this sample tube to the light. One second. The light. The light is entering through this sample tube like this. So I can say that this is the length traveled by light, optical length, optical path. Optical means light. So the light is traveling this much length in this sample tube. Naisha, every word is clear? These two things. Is it clear? Okay, good. Now let's say the light is the incident light has the energy like HV naught, right? Incident starting. But once it has entered in the tube, some amount of the light will be absorbed because you can see it's colorful. So light is absorbed, reflected like this. So some amount is absorbed here only. And the light which is coming out, this is incident, this is reflected. Refracted or reflected is by an angle. It's a physics word. So the light which is coming out. Oh yes, the word is emitted. This is emitted. Let's say that light is HV. If I represent incident light as I naught, emitted light as IT, and then absorbance is defined as, what is absorbance? The one which is not the part of emitted. Then it is defined as the ratio of the IT, the light which is emitted, which divided by I naught, IT divided by I naught. IT you can say HV, I naught you can say HV naught, HH cancelled. Isn't it the ratio of the frequency emitted over frequency incident? Emitted or transmitted. They use the word transmitted also. You can say transmission, transmitted. That is also for emitted. So can you tell me what is the unit of absorbance, children? Afan, what is the unit of absorbance? Do we have any unit here? It's a ratio of the energy emitted, energy absorbed. No units. No units. Right? Please take care of this. There are no units for A. Aditi, Lisa, and Azuni, Naisha, is it okay? Is some kind of vacation going on? Because children this week were very less. Oh, that's why. I think they are traveling. Fine. Fall break. Okay. Afan, you are a good boy. You are in the class. Because for AP, we have to work continuously. So next week also. So why don't you, people are getting so much time? Start doing quizzes. Do the review of previous classes. Recordings are there. And do the quizzes based on that. Take advantage of this break, children. Okay. And of course, enjoyment is also important, but you cannot enjoy throughout the day. So you can spend some time early morning or in the night. Okay. Yeah, that's okay. But when you are on holiday, children, we still have to think about our AP chemistry or other exams. So if you want to take out time, even on holidays, you can take out because everything is online. You just take your mobile or some kind of tab with you, and you can spend some time in the morning in the bed only. Just get up in the morning, open your tab, review one session, and do one or two quizzes, and go out, play nicely, come back in the night, review one more session, and do one more quiz. And you will be definitely five in AP. Okay? That's my promise. That if you do the quizzes regularly, you are five. Okay, so that's about your introduction of the equation. Now, how to use this equation? First of all, this equation absorbance, this calorimeter, this Beer-Lambert's law is done on colored solutions. Colored solutions has absorbance in the range of 400 to 800 nanometer. That's the visible light range, visible light in electromagnetic spectrum. So when you are going to use the instrument, so what was the instrument? There is a sample here. Sample is, generally the samples are colored. That's why it is called as colorimetry. Colorimetry. Metry means the measurement. Colorimetry. There is one cup calorimeter. Calorie. CA. This is CO. Okay. Metry word or metry you can say. It means measurement. So this is the sample here with some concentration. You are exposing this sample to light. The light which you are selecting, we are calling it as incident light. It should have a wavelength in this range if it is a color solution. If it is green color, then it should be in this range. If it is red color, then it should be in this range. If it is this color, because if you select a wavelength for that particular range uh, in which the color is appearing, we call it as lambda max. Then only you will get absorbance values. Otherwise, no. Because you see here, there is the maximum absorbance. This is absorbance here. This is wavelength. So which wavelength is good for selection here? Which wavelength? This one. You can see maximum absorbance. We call it as lambda max. Right? If you select wavelength from here or here, absorbance is there, but not maximum. So that's not going to give you very accurate values of absorbance. Absorbance is then directly proportional to the concentration. If you do error in the absorbance, then you are going to do error in your concentration calculations. So whenever there is a lab, we have to focus on errors also. So moving on, children, this is the selection of the wavelength, how to select the wavelength. This is the setup of the apparatus. Incident light, transmitted light. This is the sample. This is the length of the sample tube, L. And absorbance, which is the ratio of transmitted light to incident light, no units, right? Is equal to, yes, equation epsilon CL. What is this? It's a constant. Actually, A is directly proportional to the concentration and length of the tube. More bigger length, if you make it bigger, more absorbance. More smaller length, less absorbance, right? So it is directly proportional to this. You remove this proportional. You remember we did that ideal gas laws and all these. When a proportional is removed, we need to introduce a constant, which is this. You already know the units of everything. You know the units of everything, children? If you know the units of everything, can you tell me what will be the units of epsilon? Epsilon, which is called as, here in this particular case, is molar absorptivity. Absorptivity. So what you have to do? Absorbance is epsilon, molar absorptivity, Cl. So what is epsilon? Isn't it absorbance over C times L? What are the units of absorbance, children? No units. One. What the unit of concentration? Molar, length, centimeter. So what's the units of molar absorptivity? Per molar per centimeter. Naisha, you're there? Write it down, Naisha. Okay. Practice this. I'm sure your teacher is going to check you for this. This is how we calculate the units. So every time they will not tell you the units. Okay, and one more thing, Aditi, maybe you are just writing it fast. The molar is M is always capital, big, big M. Molar M is big, capital. Okay, so is this clear? Now this sample tube is called as cuvette. And what is the aim? Aim is to know the concentration. And from the experiment, what we are going to get? You are going to get A. Experiment will tell you A. And your aim is to know C. That is the aim. Everything is clear? So do you think if I make this solution, if I take this solution up to this level, do you think there will be any error in my experiment? I don't fill it up to the brim. I fill it only up to the part where the light can pass through it. Do you think there will be any error in my experiment? No error. Why? Because I'm using only this particular thing and this is not affected. Light is still traveling through the same length. So whether you fill it up to the brim or you fill it up to here or up to here, no error. But if I fill it here, up to here, then will there be any absorbance? No. In that case, absorbance will be zero. So the cuvette must be filled up to the level so that light can pass through it. Yes. The cuvette should be filled with the solution up to the level so that light can pass through it. If light is not passing through it, then absorbance is zero. Then you are not performing experiment. You will not get any data. So we are good with this. So you can see that I'm asking you to focus on the errors also because that's what AP is testing you for your experiments. Okay, now how to calibrate the apparatus. So the apparatus setup is like this. There is a instrument and then here you have the place. You open it and you put your cuvette in this place. And then there is light entering. It's completely closed. And light is allowed to pass through here like this. And then there is a instrument measuring the absorbance. So this cuvette is the part where the experiment is conducted. So they say you have to calibrate the apparatus. Cuvette is made up of glass. Now you have to understand, children, everything has some absorbance of light, even glass, every material. Okay, Aditi, no problem. You can watch the video after that, right? So everything is made up of material, and every material, solutions, materials, they all have absorbance. So first, when I want to calculate the concentration, I have to get rid of the absorbance of the glass, of cuvette glass. So what they are doing, they will fill this cuvette with pure water. Pure water. So here there is water. And you expose it. You will get some reading of absorbance because glass is also absorbing. Then you have a kind of knob here. You set that knob to 0. Okay. Set it to 0. Why? Because then this will ensure that anything absorbed by glass will not be reflected here. Because what we have done the calibration of the apparatus. We have made the absorbance by the water and the glass as 0. Now when I put my second cuvette with some solution and using the same apparatus which is calibrated, that apparatus will give me a reading without absorbance of glass and water. Is it okay, children? You're getting it? What is it called as, Naisha? Calibration of the instrument. calibration of the instrument. Calibrate means, I think I must have told you that we have to calibrate instruments like thermometer also. So every time we have to calibrate the instrument and we have to set up the first reading as 0 so that we can minimize the errors in the calculations. Yes, Naisha. Okay, moving on. Now, to do this experiment, your teacher will ask you to make standard solutions. You already know how to make standard solution. We discussed that. But here, we are not going to make one standard solution. We are going to make minimum 3, but you can make more than 3 also. Yes, Naisha, this is right. Calibration means just calibrating your instrument to the right scale and just minimizing the surroundings effects on the instrument or errors of the instrument. Some temperature scales, they are already in error. They show you 1 degree higher all the time. So if you know that it is already 1 degree higher, and if you are getting 25 degrees Celsius temperature, you subtract 1 from this. Okay, Aditi, that's good. Yeah, okay. I hope you're understanding it well now, Aditi. Aditi is saying she did this experiment last week. Aditi, you have to chat with me in general messages so that if you are saying something and I'm responding, then all others can also understand what I'm talking about. So she's just saying that she has done this experiment last week. And as I said, all of you are going to do it. It's compulsory to have this experiment in your AP because there are plenty of questions based on Beer-Lambert's law as lab questions. So now let's come back. Let's try to understand how many solutions we have to make. Minimum 3, maximum you can go to 5, 6, 7. But do I have to measure every time the way we followed the procedure, measure the amount, put it in that volumetric flask, add water, and when you are closer to the level, add drop by drop? So do I have to do every time? No. What you are going to do? You make only one standard solution, only one. Let's say this 2 molar KMnO4, 2 molar. Now, how to make 2 molar KMnO4? This is 250 ml. How to make it? First, you're going to calculate the moles needed. Moles is molarity times volume. Molarity is 2 molar. Volume 0.250 liters. How many moles are there? Is it 0.5? 0.5 moles. But you cannot measure moles in the lab. So what are you going to do? You will convert this into grams. For that, you need the molar mass of KMnO4, right? And you will get the grams of KMnO4. Then what are you going to do with this grams of KMnO4? You will dissolve it in some water, some amount, maybe 20, 30, 50, like this, some amount, not exactly 250. And then put it here in this flask, which is 250 ml. Then add more water, come closer to this level. This is the mark. You want to be very accurate. This is the mark. Keep adding water. When you're closer to this mark, add water drop by drop, keeping your eye here exactly at the same level. So you can see the lower meniscus, right? And once you touch the mark, stop adding water and then shake it properly and your solution is made. And what's the molarity of the solution? 2 molar, right? Now I'm asking you to make 1.5 molar. Say again, Naisha, Anil. I think Anil is talking about the number of moles. Okay, now I want you to convert, I want you to make 1.5 molar, right? KMnO4. How are you going to do it? 2 molar to 1.5 molar. You can do a dilution now. So what you are going to do? And 250 ml. This is also you are making 250 ml. So I can use this dilution law. M1, V1. You remember Aditi gave us this? Aditi is new in the class, children. I want all of you to answer like her. Lisa, all of you, please try to answer. So what is M1? 2 molar. But I don't know how much volume should I take. What is M2? 1.5 molar. And volume 250 ml. There is no need of converting this volume to liters because this is ml. So I will get this also as ml. So what is V1? V1 is 1.5, 250 over 2 ml because I didn't change this unit. How much is this? How much is this volume? Yes, children? Afan, 1.5 times 250 divided by 2. How much? 187.5. Yeah. Be accurate. Be accurate. Standard solutions. Go for maximum sig fig, right? Now what you are going to do? You will take 187.5 ml. This is the answer. You will take 187.5 ml of this solution, put it in new volumetric flask of 250 ml, add water, bring up to this level, shake it properly, and this is 2 molar, this is 1.5 molar. See, you are using dilution law. Now, similarly, you can use the dilution law again, and you can convert the molarity from 1.5 molar. I can make a solution of 1 molar, then zero point 0.5 molar, then zero point 0.1 molar. And then you can see how the dilution law can be used to make multiple solutions. Is it okay, children? So we are using dilution law to make multiple standard solutions. I made only one standard solution highly concentrated, this one, by using the weighing scale and the masses. But after that, I'm using the same solution, calculating the volume to get second one, using the second solution to get third one, using the third solution to get fourth one, fifth one. And during this process, when I'm doing this dilution law, making these different solutions, I'm conserving some amount of this. So I have now, conserving means some amount is left. You remember you took only 187.5. The remaining is left. So now I have a solution of 2 molar, 1.5 molar, zero point 0.5 molar, zero point 0.1 molar, 0.01 molar, 0.001 molar. These are the solutions with me, right? They are standard. If you do error here, your experiment will be in error. So be careful when you make when they say standard, go for maximum sig fig because this you are making. So sig figs are what you are going to decide. More accurately you measure, more higher sig fig, right? So make very accurately these solutions by using dilution law and by using that weighing scale. First solution, first highly concentrated, use weighing scale. Make it in the lab. For rest, use dilution law. Is it okay? Okay. Now children, let's go to the next part. So I'm ready with my solutions. I'm going to plug in these solutions in the instrument, this instrument. First, I'm going to plug in 2 molar. 2 molar here. And I'm going to calculate A. This is the table. In the table, this is A and this is concentration. So The instrument will tell me the A. Concentration, I know, 2 molar. So I'll get the A value, some value of A, right? Now I'm going to throw this solution. Throw it. Throw 2 molar. Wash it with water. Please now listen to my words carefully. These are experimental procedures and these are the errors also. So you throw this 2 molar completely, wash it with water, at least 2-3 times. Now pick up your another concentration, 1.5 molar. Add this 1.5 molar, only small amount. Don't fill it up to here, just small amount. Rinse it. Rinse means shake it so that the cuvette has the glass layer of the cuvette has this 1.5 molar on it. Throw it. Do it at least 2 times with 1.5 molar so that the traces of water are completely removed. See, you are understanding these things, children? Okay, now once you are with 1.5 molar, use your experiment, get the absorbance. Repeat the same thing with 1 molar. Throw this 1.5 molar completely. Wash it with water 2-3 times. Then wash it with 1.0 molar 2-3 times. And then take the reading. Get the absorbance. Then 0.5 molar, same procedure, right? So when you are doing this, you're getting absorbance and you're getting concentration. You can make a graph. If you have not done any error, you'll get a straight line. See, this is the straight line. This is absorbance. This is concentration. So you're getting a straight line, right? My experiment was different. This is different. But the readings are here. That shows error, right? See? So errors can be there, but to minimize the error, then the readings will accurately fall on the line. You'll get an exact straight line. Like this one is straight line, right? This reading is out of the line. So if you are getting very accurate straight line, it means you have done minimum errors. Okay. Now, what should I do with